Hello again. These are the notes for section 4.4, which is about something called L'Hôpital's rule. There might be some little thingies on those letters in a French style. I'm not too sure what they are. L'Hôpital's rule. This is a rule for evaluating limits. It's a rule for evaluating limits of the indeterminate type. And you're going to like it. It makes limits very easy. Rule for evaluating limits of indeterminate form of 0 over 0 or infinity over infinity. And those are our two number one indeterminate forms that we run into. Of course, 0 over 0 is the number one. Now, how does it work? So let's say we've got a limit as x approaches a, some number, whatever that might be, of some function over some other function. We're trying to evaluate that. And let's suppose that f of a equals 0 and g of a equals 0. In other words, when you plug a in, you just get 0 over 0. So we might remind ourselves over here, if you want to think of an example to sort of ground yourself what's happening here, think the limit as x approaches 2 of x squared minus 4 over x minus 2, right? Think about that example. That would be just like this, right? The f of x would be x squared minus 4, and of course, f, when you plug 2 into that, you get 0, and when you plug 2 into the bottom part, you also get 0. So it's a 0 over 0. Well, we're going to go back to our knowledge of, from, let's see, was it section 3.8, local linear approximations. Near x equals a, f of x can be approximated by a tangent line. Now, what is that tangent line? Remember, using a little bit of point-slope form, I could write it as this. It would be the slope, which would be f prime evaluated at a, times x minus a, and then on this side, this would be like my y equals, I'd have the minus f of a. I'm going to just add that to this side, like that. Okay? Now, it might be worth pausing for a minute to go ahead and try finding the tangent line to this at 2 and see how it matches up to this form. I think that'd be an excellent idea for you to pause and do that so you can see what's going on here. This is the slope, this is the x minus the x value of point slope form, and this is the y value that we added from that side over here. Okay? And also near x equals a, likewise, g of x can be approximated by its tangent line, which would be g prime of a times x minus a plus g of a. Okay, well, since the limit we're interested in is the limit as x approaches a, we're talking about values that are really, 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 really close to a. So, since tangent lines are better and better approximations as we get close to a, we should be able to, since we're getting really close to a, substitute, instead of f of x and g of x, we should be able to use their tangent lines to approximate them. That should mean that the limit as x approaches a, f of x for g of x would be the same as the limit as x approaches a of, instead of the functions, their tangent line approximations, since we're talking about things that are real close to a. So that would be f prime of a, so x minus a plus f of a over g prime of a times x minus a plus g of a. And let's see if we can simplify that a little bit. Well, remember, this is a 0 over 0 limit. So f of a is 0 and g of a is 0. So those are both 0. And if those are both equal to 0, then these cancel out. That's the x minus a. That's the thing that's causing the 0 over 0 problem, right? So we get those to cancel out. We just end up with the limit as x approaches a, f prime of a for g prime of a. Whoa, so check that out. That means that the limit as x approaches a, some rational expression like this, if it's a 0 over 0, remember, if it's not a 0 over 0, then this would not have happened, and we couldn't have done this canceling. But if it is a 0 over 0, those cancel out, the x minus a's cancel out, and we just get, it's the same as the limit as the derivative over the derivative. Well, that's pretty crazy, and that's a good trick. So let's try it. Of course, we can do this one by factoring and canceling, right? But let's try it doing this new trick. That means the limit as x approaches 2, x squared minus 4 over x minus 2 is equal to the limit as x approaches 2. Of course, first you have to check and make sure it's 0 over 0. Of course it is. So that means I just take the derivative of the top, it's 2x, over the derivative of the bottom is 1, and now I can plug the 2 in. It's 2 times 2 over 1, which is 4. Bam! How about that? And of course, we know by factoring and canceling that it's the same thing. Now, notice that we're not using the quotient rule here. We're not taking the derivative of the whole thing. We're taking the derivative of the top and the derivative of the bottom separately. Okay? This has nothing to do with the quotient rule. This is something that says if you've got a 0 over 0 limit, it's the same as the derivative of the top divided by the derivative of the bottom. Plug in your a. Okay? Now, listen. You're not going to see a whole lot of examples that are this easy in the BC, Calculus BC curriculum. You will see some examples that are more difficult, and we'll get to that in a second. Some of them, sometimes, let's see if I can find it, figure a limit. How about this? Let's see if at this late hour I can make one up that will work here. We'll put x squared on the bottom. And then on the top, we'll put, how about, x approaches 0 of cosine of x minus 1. Let's see how that works out. Okay, so we plug in 0. Cosine of 0 is 1, minus 1 is 0, 0 squared is 0. Okay, so we use L'Hopital's rule, which says if it's a 0 over 0, then take the derivative of the top, which is sine x. Oops, a ladybug just landed on my iPad. Want to see? Oops. There it is. Sine x over 2x, and then if I plug 0 in here, I get 0, sine of 0 is 0, and 2 times x, that's 0. I get 0 over 0 again, so I can use L'Hopital's rule again. And, oops, I'm sorry, I made a sign mistake, didn't I? The derivative of cosine x is negative sine x, excuse me. And limit x approaches 0. So now we take the derivative again. The derivative of negative sine x is negative cosine x over 2. And let's see, now I plug in the 0. That's negative 1 over 2. That's negative 1/2. So if you get 0 over 0 again, you just use L'Hopital's rule again. And now just to show you, limit as x approaches 0, sine x over x is, remember we learned in chapter 2 that this limit is 1, right? But now we've got an easy way to do it, or confirm that anyway. So the derivative, well, we plug in 0, it's 0 over 0. The derivative of sine x is cosine x over 1. And then we plug the 0 in, and we get 1. So sure enough, using this technique, we get the same answer. You might be wondering, didn't I say that it also works for infinity over infinity? It does. You can do the exact same trick. Does the proof still work? Well, it does. You just have to turn over infinity over infinity. If you flip things over, can be easily turned into 0 over 0. And I think that'll become clear in the next couple of examples. So let me show you an example. It's a little more difficult. And this is the kind that you tend to see pop up on the AP exam. Let's try the limit as x approaches infinity of x plus 1 over x to the x. You may recognize, oops, I'm sorry, that should be 1 plus 1 over x, is what I meant. If it was x plus 1 over x to the x, that would obviously blow up to infinity. This would get really big, the power would get really big. Not interesting. But this one, I mean, what indeterminate form is this? If you try to plug infinity into this, it looks like it's trying to be equal to 1 plus 1 over infinity. 1 over infinity is like 0. So that's like it's trying to, something that's going to 1 to the infinity power. And you might say, well, duh, 1 to the infinity power is just 1. But remember, just like 0 over 0 is indeterminate, this is also an indeterminate form. Because it all depends on how fast you're getting to 1 and how fast this is going to infinity. So the trick is here, this is not the kind of indeterminate form that L'Hopital's rule can deal with. L'Hopital's rule likes 0 over 0 and 1 and infinity over infinity. So somehow we need to do something to this to make it into one of those. And this is how we're going to do it. We're going to make an equation out of this so I have two different sides to work with, okay? And show you what I mean. And say, let's let y, or actually, let's not make it look like a function. Let's let L, we'll say that's the limit. The answer that we're looking for is L, right? Let's let L equal the limit as x approaches infinity of 1 plus 1 over x to the x. Then I'm going to take the natural log of both sides. Why would I do something crazy like that? Because if I take a natural log of something to a power, this gets to move to the outside, right? So let's move that down. Actually, I better keep this in here like that. Okay, I can't move the x out of that because x is going to infinity, so that can't cross the limit barrier. Okay, so now what good does that do us? Well, let's see, natural log of L, our limit is equal to. Now what have we done here? We've taken the exponent and we got it to go out to the front. So now we have infinity times the natural log of 1 plus 1 over infinity. Remember, this is going to 1, right? Natural log of 1 is 0. So I've turned this into infinity times 0. Okay? Now it's an infinity times 0. Well, this is one short step from being, remember, if I could take that infinity, couldn't I take that and turn it into, leave the 0 on the top and move the infinity to the bottom? Of course, you can't just move things to the bottom of a fraction, but multiplying by that is the same as dividing by its reciprocal, right? So you might want to pause after I write down this step and make sure that you're okay with the algebra. That's the same as the natural log of 1 plus 1 over x over 1 over x. So I took this x and I moved it to the bottom by flipping it over. It might be easier to see how to get from here to here. Dividing by 1 over x is the same as multiplying by x, right? Dividing by a fraction, same as multiplying by the reciprocal. Okay, so now I think this, as x goes to infinity, this goes to 0. As x goes to infinity, this goes to 0. We've got it into what I would call a L'Hopitalable form, right? We can use L'Hopital's rule on this. So let's try it. Now we're going to take the derivative of the top and the bottom. So this says that the natural log of my limit, remember now we're on this side of the problem here, we have the natural log of our answer, right? Because we took the natural log both sides. We'll have to deal with that when we get the answer. So let's see, the limit as x approaches infinity of the derivative of the top. Let's see, what's the derivative of this? The derivative of the top would be 1 over, the derivative of natural log of whatever is 1 over whatever times the derivative of what's inside. The derivative of 1 is 0. The derivative of 1 over x, that's x to the negative 1, is negative x to the negative 2. Right? And then the derivative of the bottom is negative x to the negative 2. So those cancel out. I plug my infinity in here, and I get 1 over 1 plus 1 over infinity. 1 over infinity goes to 0, so that's 1 over 1. That's just equal to 1. That means that the natural log of my limit, that's the answer we're looking for, right, is 1. And then rewriting this, remember this is log base e, that means L is equal to, sorry if I lost you there for a second, L is equal to e to the 1, or e. So the limit as x approaches infinity, 1 plus 1 over x to the x, is e. And you remember we just proved something that you learned in pre-calculus. You learned in pre-calculus, this is that interest compounding continuously expression. This is where the PERT formula came from looking at this. And we never really, we just kind of looked at that and said, yeah, we compound more and more times and kind of goes to E. But we never really were able to prove that. Now you can prove that. So let me sum up by saying this. If you're wondering to yourself, at least relative to like the easier limits, like this one, right? If you're wondering, how come, Mr. McGrath, you didn't tell me about this before? Because that's so easy to do. And of course the answer is, think about it. You didn't know what a derivative was, right? In Chapter 2, when we were doing limits, and last year when you did limits, you didn't know what a derivative was. So I couldn't have taught you L'Hopital's rule. But now you do. And now you know. And that's L'Hopital's rule.